Hi, this is the second video of our limits and continuity. We begin with just evaluating limits algebraically. Now, we discussed in the first video that the limit as x approaches to a of f of x equals to L. As we go through the different x values, as it gets closer and closer to a, it approaches this y value we call L. And for most of the cases, we don't have to look at a table. We sometimes look at a graph, but for the most part, we get to evaluate it algebraically. For most cases, we can generalize limits to then this. Because most cases, I can just notice it on the graph, it just looks like I can just plug it into the function. That the limit as x approaches to a of f of x can be just me plugging it in when x equals to a. This red section here says, note that at times, f of a might not equal to L, right? There might be some error or there might be some problems, but it can approach L. We're going to discuss that later on, what that means. But let's say for this example, the limit as x approaches to 3 of 2x squared plus 4x minus 1. So I know for a fact that this looks like a parabola. And I know that it can approach x equals to 3, that clearly there is some value that it can go. And so how do we do this? Well, one of the ways that we can easily do this is just plugging it in. So for most cases, we can just say the limit for this, I can just plug it in. I can say 2, 3 squared plus 4, parentheses 3, minus 1. I don't have to look at the table. I don't have to look at the graph. All I can do is just simply plug it in algebraically. When I do that, I'm going to evaluate it. So 2 times this would give me 18 because 3 squared is 9. 2 times 9 is 18 plus 12 minus 1. All of this in total gives me 29. So we can say the limits as x approaches to 3 of our function gives us 29. Let's try it one more time. So I can see here, this is like a random rational, but in any cases, if you can't see it graphically, just plug it in and see if it can give us a value. When I do this, this gives me the square root of 2, parentheses 2 squared, plus 1. On the top, on the bottom, it gives us 3, parentheses 2, minus 2. What would that give us? Well, on the top, we get the following. We get 8 plus 1, because 2 squared is 4. 4 times 2 is 8. 8 plus 1. And then on the bottom, we get 6 minus 2. What would that give us? This would give us the following. 9 plus 1 is 4. 6 minus 2 is 4. Then I just calculate the square roots. The square root of 9 is 3. The square root of 4 is 2. So we can make the claim that the limit as x approaches to 2 for this particular function equals 3 over 2. Now, there are some cases where it might not be that way. So sometimes we can plug it in, and it's just f of a, but there are some weird cases. And we're going to begin with this first one, that the limit as x approaches to 5 of this entire function. Okay, let's just say I did plug it in. When I do plug it in, I get on the bottom 5 minus 5, while on the top I get 5 squared minus 6 times 5 plus 5. Now I'm just going to plug it in like normal, and I'm just going to see what I get. On the bottom, I get 5 minus 5, which is 0. And then, well, on the top, if I do it again, that also gives me 0. Can I do 0 over 0? No. And I'm completely confused about that, right? Like, that doesn't make sense. 0 over 0. Do I just end there? I say there's no solution? Not quite. So this is one of the weird cases in limits where I kind of mentioned it in red, that the limit can sometimes doesn't equal to L, but it can approach L. And we're going to figure out one of the ways that we can do that using algebra. And so let's just establish the weird case. There are some weird cases that the limit as x approaches to a of f of x can sometimes be 0, 0. And how do we escape that? When we see this 0 over 0, one of the first ways that we can try to solve this is by factoring. So let's just try factoring for this first part. Notice how this video is going to be part 1, so there might be some other parts. So if I'm trying to look at this, I notice that there's an x minus 5. That's what caused it to make it become 0. Here's what I can do. what I can probably do is take and get rid of that x minus 5. I don't really like it because it would give me that 0 on the bottom. So if I want to get rid of that x minus 5, in order for me to cancel it or kill it, one thing I need to do is I need to also have x minus 5 on the top. Something like this. So that in the end, I can kill them out. But then how do I do that? Well, one of the things I can do is I notice that, hey, the top is x squared minus 6x plus 5. Maybe one thing I can do is I can factor. And so let's just see how I can factor. So in this case, for x squared minus 6x plus 5, remember this is the x method. For x squared minus 6x plus 5, negative 6 can go on top, 5 can go on bottom. And the two numbers that I can make 5 are 1 and 5. And since it's negative 6, I can make them both negative. And so this gives us our factor form, x minus 1, x minus 5. And so let's rewrite that. So I'm going to rewrite that for our limit. The limit as x approaches to 5 is, well, x minus 5 times x minus 1 over x minus 5. And notice what that changes. Instead of now having 0 over 0, I notice the top and bottom, they can cancel out. And so the x minus 5 is no longer there. Our problem that caused 0 over 0 is no longer there. So now all we have when I factored is the limit as x approaches to 5 of x minus 1. And then guess what? What I can do again is I can basically plug it in. This would give me 5 minus 1, which gives me 4. Notice we used to have 0 over 0, and it didn't look like it equals to a value, but we can say that this function in itself approaches 4. We're going to try it one more time. And don't worry about if this is really confusing. We're going to have a lot more videos and a lot more examples to kind of go through this. We have here, for example, the limit as t approaches to 1. And for our cases, we have our function. We have t to the power of 3 minus 1 over t squared minus 1. And so what we're going to do is that we're going to try to be able to notice some things. Can this give me 0 over 0? When I do that, I'm going to get 1 cubed minus 1, 1 squared minus 1. That's just basically saying 1 minus 1, 1 minus 1. That's definitely 0 over 0. So we're in deep trouble. Well, again, we have to ask ourselves what's causing that to be. If you notice in the last one, we said that x minus 5 was our problem. And so we can do the same logic here. Instead of saying just the t squared minus 1 is t squared minus 1 is our problem, maybe it's just t minus 1. And then what did we do in the last one? Well, in the last one, we killed it, right? We killed our problem. We had t minus 1 on the top and bottom. Now we can probably kill it. So we just need to figure out what kind of ways can we factor those out and then maybe get our limit. Luckily for this, the bottom, it's not too hard to factor. We notice that this is a difference of squares. And so what I can do is I can just say that's t minus 1 and then t plus 1. For the top, it's going to be the same thing. What am I trying to get rid of? I'm trying to get rid of t minus 1. So I'm going to have that on the top. Now, again, how do I factor the next part? This is what we call the difference of cubes. The way I like to think of it is like this. If I write t here and there's t cubed, it's going to be t squared. And then what I can do is I notice that this is a minus 1. In order for us to keep that minus 1 for our factored form, this is going to be plus 1. And I usually like to say this. Since for the difference of cubes, I like to say it's plus t, that everything is positive versus this being negative. That's my general way of figuring it out. Now that I have it factored, what can happen? They cancel out, leaving me with the limit as t approaches to 1 of our function t squared plus t plus 1 over t plus 1. And I can now plug it in and see if I can get something. 1 plus 1 over, that's the bottom, 1 squared plus 1, giving me 3 over 2. There we go. Now we no longer have 0 over 0, but rather an actual value, 3 over 2. And so that's kind of the basics of how to evaluate limits algebraically. I know we only went through 2 examples of the weird cases, and I will say that for our course, there's a lot more weird cases. But don't worry, we're going to go through all of them and see how we're going to do that.